This video is for topic 8.4, acid-base reactions and buffers. The objective for this topic is to explain the relationship among the concentrations of major species in a mixture of weak and strong acids and bases. So we're going to look at all of our different combinations. The first one we're going to look at is the combination of a strong acid and a strong base. So remember, strong acids and bases completely ionize or completely dissociate in solution. So that means our strong acid is going to completely turn into its hydrogen ion and its corresponding anion. And the base is going to turn into the hydroxide ion and its corresponding cation. The anion and cation from the acid and the base are going to be spectator ions. They're not going to react. So we simply end up with the hydrogen ion reacting with the hydroxide ion to form water. The pH of this solution is determined by whatever is the excess reactant. So hydrogen ion and hydroxide ion react in a 1-to-1 ratio to form H2O, to form water. And so if we have more acid than base, then the pH is going to be determined by the concentration of the acid. If we have more base than we have acid, then the pH is going to be determined by the concentration of the base. So now we're going to look at a combination of a weak acid and a strong base. So a weak acid we often abbreviate as HA, A being the generic anion, H being the proton or the hydrogen that acts as the base. So a weak acid and a strong base is going to form an equilibrium because the acid is not going to completely dissociate. So the acid is going to break apart into its hydrogen ion and the acid anion. The hydrogen is going to react with the hydroxide from the strong base to form water, and then you'll be left with the anion from the weak acid. So pH is again determined by which is in excess, but this gets a little bit more complicated. If the weak acid is in excess, we form what is called a buffer, and a buffer is a solution that resists change in pH. The pH is then determined using an equation called the Henderson-Hasselbalch equation. If the strong base is in excess, the pH is determined from how much excess there is and the total volume of solution. So you'll use stoichiometry to determine the moles of excess hydroxide. You'll look at the total volume of solution, and that will get you your concentration of the hydroxide ion in the total mixture. Then you can use that to calculate your pH. If they are equimolar, so that means you have the same amount of weak acid and strong base, the pH is determined from the equilibrium. So that's where we have to look at the reverse equilibrium of the acid anion then reacting with the water that's in solution to form the weak acid and the hydroxide ion. So then we will use our ICE table to determine the pH based on the remaining concentrations. A weak base and a strong acid is a similar type of combination, but let's talk about the notation. So we often abbreviate this as our base with a capital B, and we often show this with our hydronium ion because a base is going to accept a proton. So our hydronium ion is going to give up a hydrogen ion to the base to be considered a weak base. But not all of that is going to happen. And so we're going to be left with the original base, the hydronium ion, the conjugate acid, which is Hb+, as well as the water that's in solution. Again, if the weak base is in excess, we form a buffer, so it's going to resist changes in pH, and we can use the Henderson-Hasselbalch equation to determine the pH. If the strong acid is in excess, so we have more of the hydronium ion available, then we're going to look at how much excess hydronium we have and the total volume of solution. So again, we're going to use stoichiometry to look at how much excess hydrogen we have and the total volume of solution to determine our concentration of excess acid, and then we can use that to determine our pH. And if they are equimolar, so we have the same amount of weak acid and weak base and strong acid, then the pH is determined from the equilibrium of the weak conjugate acid reacting with the water to form the original base and the hydronium ion. And then our last combination is a weak acid with a weak base. And so we form an equilibrium where we have our weak acid giving up some of the hydrogens to the base, and we form the conjugate base, which is the anion from the acid, and the conjugate acid, which is the protonated form of the weak base. This probably looks very similar to the strong acid, strong base reaction. However, since these don't completely dissociate or completely ionize, it's going to be in equilibrium because we're going to be left with some of each of the species in solution once we've reached that equilibrium state. So it's important to not only analyze what your reactants are, but it's important to know what your reactants are going to do in solution, because that's going to help you determine how you are going to evaluate the pH. So it first matters whether they're weak or strong acids or bases, and then it's going to matter which one is in excess, because which one is in excess is going to tell you how you will determine the pH of the final solution.